For our second example, we're going to use Gaussian elimination to solve the system 4x plus 4y minus 8z equals 0, 2x plus y plus 3z equals 6, and negative 2x plus 4y minus 5z equals negative 3. That is to say, we're going to solve that thing that we started with that wasn't so obvious, but leads to a nice solution at least. So the first thing we're going to do is we're going to take that system, not so nice, and turn it into a augmented matrix. Because it looks a little prettier, but that's also not so nice. It doesn't really tell us anything about what we're going to do here. It just is. Well, what we can do then is think about our row operations, about how we can make this into what we need. And when we're thinking about row echelon form, when we're thinking about Gaussian elimination, remember that our ultimate goal is to get ones along the diagonal, zeros below. If we want ones along the diagonal, looking at these pieces, well, geez, the second two don't have any nice common factors. The first one has a 4, so you might want to get rid of it, but actually you got a 4, and an 8, so that might be your best bet to work around. What you can do there is take that first row and apply a constant multiplication to it to get a 1 there. That's step 1. To get the 1 in that first part of the diagonal. From there, what you want to do is clear out the rest of that first column, because you want zeros below the 1, right? So to do that, if you got a 1 up there, you got a 2 below it, you're going to need to subtract 2 R1s to get rid of the 2, and you're going to need to add 2 R1s to get rid of the negative 2 in the third row. When you're thinking about making these reductions for Gaussian elimination, and later we'll see something called Gauss-Jordan elimination, you kind of have to be a little unconcerned with what happens to the other terms along the way. You're just focused on what gets rid of the things directly in front of you in your path towards a row echelon form matrix. So you can get rid of those two down there, and in the process, you're going to have to make some adjustments for the others, because you can't just remove the single term there. So when you subtract 2 times R1 from R2, in the second entry, that means you're going to be subtracting 2 from the 1 in the second row. So you get 1 minus 2, negative 1. And then negative 2 times negative 2, so you get positive 4. And you're going to add that 4 to the 3 to get 7. And then, thankfully, the last part's pretty easy because you're adding 0, multiplying by 0. Doesn't do a whole lot. You still just get 6. So the hardest part with this type of thing, once you get past the identification stage, is just being really careful following through on that arithmetic. There's a lot of it, but once you get the first bits down, it's not so bad. You just, again, have to be careful with those details, but you should end up with your second row in form 0, negative 1, 7, 6. I've got too many of these matrices on my notes. It's easy to make mistakes, but that's where you should end up after that operation. And then in the next one, you're going to be doing the same sort of thing, but down to row 3. So you're going to have 2 times row 1, 2, plus that value in the bottom there, so negative 2 goes away. Then you're doing the same thing with the 1, adding that to the 4, you get 6. Then you do it with a negative 2 along to a negative 5. So you get negative 2 times 2, negative 4, minus 5, minus 5. Too many minuses, but you get negative 9. That's the long and short of it. And then 2 times 0 is 0, plus negative 3 is still negative 3. So what you're going to end up with after all that is something of this form. Again, lots of simple steps, but there are a lot of them, so you just have to be careful. Anyway, once you have that, your next goal is to figure out how you can get a 1 in the second row, second entry. You're going to keep that diagonal pattern going. Well, you got a negative 1 there. So there's actually not that much to be done in terms of putting that guy where it needs to be. You just put in a term of negative 1. You multiply through. So negative 1 becomes 1, 7 becomes negative 7, and 6 becomes negative 6. That's not so bad, but now you've got a nasty little reduction at the end, because you got 6 that needs to become a 0, so you're going to be subtracting 6 times the second row from the third row to get rid of it. Do that, and what's going to happen is, well, the 6 goes away, but then you have negative 6 times negative 7, so you get positive 42 plus negative 9 gives you 33. And then unfortunately you don't have two zeros to work with here, but what's going to happen is you have negative 6 times negative 6, you get positive 36 minus 3 gives you 33. So your final row for those big numbers is actually pretty nice. It's just two 33s, knock out the 33s, and you get 1s. So what you end up with is 1, 1, negative 2, 0, 0, 1, negative 7, 6, and 0, 0, 1, 1. Not the cleanest picture, admittedly, but you can turn that back into a system where your system would then be equivalent to that original kind of nasty one and is now x plus y minus 2z equals 0, and then 7, y minus 7z equals negative 6, and z equals 1, which means you can do a direct substitution right off the bat there. Z equals 1, great. Plug that 1 into the equation for y minus 7z, you get y minus 7 equals negative 6. Add that over, y equals 1. And then finally, once you've got x and y, y and z, it's too many letters. You plug them into that first equation, you have x plus 1 minus 2 equals 0, which tells you that x also has to equal 1, just like I said however many minutes ago that you end up watching this video. So you end up with your final answer of 1, 1, 1 as desired.